It's with great pleasure that I have the honor of introducing our plenary speaker for today, Miguel Onorato, and he will be talking about anomalous conduction in chains, the wave kinetic approach. The stage is yours.
Thanks a lot, Matteo, and thanks to all the organizers. I hope really that we will be able to see each other next year all in Cambridge. So first of all, let me acknowledge my collaborators, Giovanni De Matteis, who is in Rensselaer Polytechnic Institute. He was a former postdoc of mine, and now he's working with Yuri Lvov. Then he's also a collaborator of this talk. Lamberto Rondoni from Politecnico di Torino, Davide Proman from Norwich, and Francesco De Vita was a former postdoc, now at the Politecnico di Torino, and Raffaele Mazzilli, who was my master's student, and now he's in Stuttgart. So I will talk about the problem of anomalous conduction in chains, which is a topic that has been discussed quite a lot in the literature. And what I will present is just some contribution that we gave recently by doing some numerical computation at a microscopic level, so simulating the equation of motion, and also at the level of the wave kinetic equation. So just to say, just to make a remark, what I will talk about is the transport properties of a system of masses and springs, okay? And I will do this in the limit of very small nonlinearity. So I will do really the statistical mechanics of a system of weakly interacting waves, which is somehow the opposite limit with respect to what has been discussed last week, for example, by Pierre Fourier or Stéphane Rondeau or Doyon, in which the interest was basically mostly on integrable system and solid on gas. Okay, so keep in mind that we are working in the opposite limit, so it's a weakly nonlinear system, but even if these weakly nonlinears are, as you will see, is still very rich and to me very interesting. Let me just give you some motivation and some for the work that we have done. And let me start with something that I'm more familiar with, which is fluid mechanics, and then I will move to solid state physics. Okay, so we all know that if we want to describe a fluid from a macroscopic point of view, we use Navier-Stokes equation. Okay, here is the Navier-Stokes equation, which I'm sure that you are familiar with. And this U is, it's not, of course, the velocity of a single molecule or a single atom, but it's the velocity of a particle of fluids, which is a suitable average over volume, over all particles containing a volume, which should be sufficiently large that contain many particles, but also small with respect to the size of the system. And in this equation, you also see that nu is the viscosity and its transport coefficient. Okay, this is from a macroscopic point of view, but of course you can have a description which is microscopic, and in that case you need to work with the Newton's law. So the idea is to write a Newton's law for each particle in the system. And of course, this is something very complicated, and you would not be able to do to solve anything concerning fluid mechanics using this Newton's law. In between the microscale and the macroscale, there is the mesoscales, and there is the Boltzmann equation, where F is a distribution function of the velocity of the particles, it's a function of x and velocity. And on the right-hand side of this Boltzmann equation, you see this C of F, which is a the collision integral. So this term on the right-hand side takes into account the elastic collisions between particles. As you see here, I have put some epsilons here, okay? And those are the epsilon that should be put in order to derive the Navier-Stokes equation. So going from Boltzmann equation to Navier-Stokes equation, there is some particular scaling that you need. And indeed, what you observe from here is that the collision integral should be a dominant term. So it's really important, and you should keep this in mind through all my talk, the fact that collision integral is fundamental because it keeps the system in local equilibrium. And this is fundamental in order to get the macroscopic scale, so the Navier-Stokes equation. Let me just make one more remark, and all this has been studied quite a lot. I mean, as a physicist, we are very used to all this, but from a mathematical point of view, there are rigorous results. Just to mention something, for example, Lumford about the validity of the Boltzmann equation, of the more recent results by Saint-Raymond or Gallagher. Okay, so this is the let's say the perspective from in fluid mechanics, but what happened in a solid state. So let's consider a crystal. Okay, let's suppose that we have a crystal again. The simplest model, of course, if we want to do something more accurate, we should include also quantum mechanical effects. But first approximation is that again you can think as a crystal just by writing down the Newton's law. Okay, and at a macro scale, it's well known that we have Fourier's law, and here is which is the law of heat conduction. And here the Fourier law says that J, which is the flux of energy, is equal to the gradient of temperature, and there is a constant kappa E, which is the thermal conductivity. Okay. Now, if you apply, and kappa E is does not depend on the size of the system, may depend on the temperature. And if you apply conservation law for energy, okay, we all know that starting from the Fourier's law, we end up with the diffusion equation for temperature. So this is what we all know. And if kappa is constant and C are constant, C is the heat capacity, then this is classical diffusion equation. What is in between the microscale and the macro scale? Okay, this is much less investigated with respect to the Boltzmann equation. And I have, and maybe not everybody agree, but what I have written here is the wave kinetic equation. And I have put here some picture of people who mostly, according to me, contributed to the development of the wave kinetic equation. And the first one is Peierls, that in the 20s last century, so about 100 years ago, he wrote down the Boltzmann equation for phonons. And then we have Klaus Hasselmans, also who derived from water waves equation, the energy transport equation for water waves, which is a kinetic equation, and also, I mean, Zaharoff gave an enormous contribution to the understanding of the wave kinetic equation. From a physical point of view, I'm used to this kind of equations, but from a mathematical point of view, I should point out that the derivation of the wave kinetic equation, starting from any, let's say, wave system, is still an open question. And just very recently, some new results came out by Hani Zaher, who derived, starting from NLS in 3D, in dimension 3, at least 3, so greater or equal than 3, he was able to make a derivation, a full derivation, rigorous derivation of the wave kinetic equation. This is something that has been put in the archive just some months ago. Okay, so we know much less about this wave kinetic equation that we know about the Boltzmann equation for particles. Also, going from wave kinetic equation to Fourier's law, I'm not aware of any rigorous result in terms of mathematics. But in any case, if we assume that the Fourier law is valid, then let's suppose that we want to study the problem of two thermostats. Okay, we have two thermostats and we have a solid in between. Then it is well known that the system, once we have reached a stationary state, the temperature is linear inside in the solid. So the temperature decreases from the thermostat at larger temperature to the thermostat at lower temperature in a linear way. Okay, so this is something that I guess we all know, but what about anomalous conduction? What about the breakdown of the Fourier law and anomalous conduction or anomalous transport? Okay, these transport coefficients, like take for example resistivity in an electrical wire. We all know that, I mean, if you increase the length of a wire, okay, and electrical wire, the resistivity should not change, because resistivity is an intrinsic property of the material and should not depend on the size of the material or length of the wire, or length of the wire. And this is also what we expect from Fourier law. However, just more recent, I'm saying recent, but it's already probably 30 years ago, there has been a lot of intensive numerical work and also experimental work more recently that show that actually this thermal conductivity may be a function of the length of the wire. This happens in low dimensional system, which basically means in one-dimensional system, okay, in nanowire, for example. So kappa E is the conductivity, is a function of the length of the nanotube, for example, nanowire, and scales like L to some power alpha. Of course, if alpha is 0, then kappa E is a constant, and we're all fine with the Fourier law. However, if alpha is a numerical results show that alpha can be between 0 and 1, and this is what is called anomalous conduction. Okay, so and for alpha equal to 1, this is what they call ballistic conduction. This problem of the divergence of the conductivity is also related to the fact that if we, for example, take a Gaussian function and we solve the Fourier, for example, law, the diffusion equation, we expect that the standard deviation, that the width of the Gaussian would diffuse, and that the sigma, the standard deviation, would grow like a square root of time, right? We all know that. However, it has been observed that there are some systems, again, for which sigma square scales like t to some power beta with beta greater than 1. So those are super diffusive systems. Let me give you some numerical and experimental evidence of this. Okay, first of all, I took this from a very nice book. So there is a book, it's Lecture Notes in Physics by Stefano Lecri, which is a collection, quite recent collection of papers, all related to anomalous conduction. So I took some of the picture from it. And this is the case of a one-dimensional system characterized by masses and springs in between two thermostats. Okay, so you have two thermostats which are placed at a distance L. So basically the first mass has a kinetic energy which is larger than the last mass. Then you let the system evolve, you reach some stationary state, you compute the fluxes, and then you're able to compute the conductivity coefficient. And then if you do experiments by changing the distance between the two thermostats, you get that the kappa, the coefficients, is a function of L, and it scales like L to, now here they put 0.35, which is this straight line here. So this is a numerical evidence of anomalous conduction. Another example here is hard point gas, okay? And this hard point gas which is a one-dimensional system in which you have masses, but there are alternating masses, not all the same. If you start with the time t equals 0, you put a Gaussian function, then you, as I mentioned, you expect that this would increase its variance like t to power like t. Indeed, that it does not happen. What happens is that the system creates this oscillation here, and then it scales like 3. The standard deviation scales like 3/5, 3/5, rather than 1/2. Okay, so this is another example in which you have anomalous conduction. About experiments, these are experiments which are discussed in this paper, which is included in the book of Lepri by Chang, 2016. So the experiments are made with silicon germanium nanowires. This is just a sketch, so this is not a real experiment, but the idea is to put a nanowire of silicon germanium in between 2 thermostats, of course, at different temperature, and then somehow they're able to measure thermal conductivity, and they plot thermal conductivity as a function of the length of the wire. And as you can see here again, that the thermal conductivity changes as the length of the wire changes, and then up to some length, and then it becomes constant. And basically, when it becomes constant, it means that the Fourier law works. Okay. Oh, some other numerical evidence. Also, the profile of the the temperature profile when you have anomalous conduction is different from what we expect. And then this is an experiment that has been done using a system of masses and springs, but just using harmonic potential. So basically, this is a linear system. And according to the Fourier law, you would expect a line here, a straight line from here to here, but actually this is not what happens. There is a fast drop of the temperature in the first sites, then the temperature is constant, which is an average between the two thermostat temperatures, and then it drops down. So this is the typical profile, temperature profile that is observed for linear system, which do not display a Fourier law. If you include, oh, what is happening? Is this okay? You still, sorry. If you include nonlinearity in the system, and you again place your system in between two thermostat, you get something which is closer to the Fourier law, so the strain length, but not exactly that. Okay, so something really is happening, and indeed, this is what I want to talk about, and I want to try to explain from a physical point of view, which is the origin of this anomalous conduction. Both in terms of simulation of the deterministic equations, but also from a kinetic, wave kinetic approach, so using the wave kinetic equation. Okay, so the model that I will consider is a model of masses and springs. This is the so-called beta FPU system, in which we have n masses connected. So this is J mass J, which is connected to J plus 1 and J minus 1. Forces are just, this is the standard Hooke law, and then you have an extra term here, which gives the nonlinearity of the system. So this system is Hamiltonian, kinetic energy, harmonic potential energy, and then you have this anharmonicity here. Already Fermi understood that anharmonicity was a fundamental ingredient in order to have a regular conduction a la Fourier. The system has been widely investigated, so I will not go into the details, but of course, there is a huge amount of literature in this FPU T system. Just here is the equation of motion. Okay, so here is the equation of motion. So Q dot dot, and this is the linear part, and this is cubic nonlinear part. So if you want this system can be reduced in some limit, in the long wave limit, to some sort of modified KDD equation, if you look at waves going in one direction, or if you take some narrow band approximation, you can write down the analysis equation starting from this model. Dispersion relation, I mean, you can compute dispersion relation, of course, the linear dispersion relation, and this is omega k is given by sine pi k over n. So this is limited. It's a bounded dispersion relation. Note that because it's discrete, because the model is discrete in physical space, then what happens is that the Fourier space is periodic. So we have a k max, we have a Brillouin, this is called Brillouin zones, but it's periodic in Fourier space. Okay, but as I mentioned you, I'm interested in conduction, the problem of conduction, and in measuring the thermal conduction of the system. So what we have done, and this has been done also by many other people, so this is not say an original contribution. We consider two thermostats, and the way we do it, we place on the right hand side of the equation of motion with this term B, okay, this term B, which it contains some 2 Kronecker delta, so it applies only at the first mass and at the mass n, capital N. So the first and the last mass, you have this extra term in the equation of motion. And what do they look like? Well, the idea, the physical idea, is that you shake the first mass with some kinetic energy, P1 square, and if this is larger than your temperature, okay, what is happening is that this mass will be damped. If it is not, if it is lower temperature, then its kinetic energy will be increased, right? So this is how this thermostat, this is a deterministic way of doing the thermostat. It's called Nose-Hoover thermostat. Okay, but let me tell you what is our strategy in order to understand the problem. Okay, well, first of all, the problem between two thermostats is not homogeneous. Okay, so you have, if here you have a thermostat and here you have another thermostat, in between the temperature should change, right? Should gradually change from one thermostat to the other. This means that, this means that it's, even though people do it, it doesn't make any sense to take, for example, Fourier, to do a Fourier analysis over the whole domain, because this is not periodic, right? So what we decided to do in the spirit of understanding the things from a mesoscopic and macroscopic point of view, we decided to divide our system, okay, in boxes. And those boxes contain, each of them contain a large of scale lambda, and each of them contains a large number of masses and springs, right? So for each box, you have a large number of masses and springs, but of course, L is the length of the chain, and L over lambda goes to infinity. So L, we take L just to have a separation of scale that goes like lambda to the power of 2. And in this way, we are able to measure locally the properties of the system. In particular, what we want to do, we want to study the spectral property, the spectrum in terms of the Fourier properties of the system in each box. Okay, so this is the idea, because this is exactly what the kinetic equation does, as I will tell you later. Let me show the results on this. Okay, so I need to explain this slowly. Okay, so these are the energy spectrum, the symmetric part of the energy spectra, because only the symmetric part contribute to the total energy of the system. Okay, because the integral of the non-symmetric part goes to 0. And here is wave number K. Okay, I show only the wave number from 0 to pi, because the other is of course symmetric. I show here 2 lines, a red one which comes from computation, and a blue one. The red one corresponds to spectra computed very close to the hot thermostat. So basically, we are here, very close to the hot thermostat, and we take a box of size lambda, and we take Fourier transform of that, and we do Fourier analysis, right? The other one, the blue one, is computed close to the cold thermostat. What do we expect? Okay, as I mentioned to you, the macroscopic dynamics is obtained once the system is in a thermalized state. What does thermalized state means? It means that according to statistical mechanics, what we expect is to see an equipartition of energy among the Fourier modes. Indeed, what one would expect, what one would expect is that to observe something, this dash red line. This dash red line would correspond to equipartition of energy close to the thermostat, hot thermostat. And this blue line would correspond to equipartition of energy close to the cold thermostat, right? So indeed, what we observe is that for high frequency, there is good agreement between our numerical results and what we expect from standard statistical mechanics. However, for long waves, for low wave numbers, it seems that waves have the same temperature, which, I mean, independently of the fact that they are close to the hot thermostat or to the cold thermostat, they have exactly the same temperature. So this means that there are some waves that travel from one thermostat to the other without interacting with the rest of the waves. And this can be explained within the kinetic, wave kinetic theory, and I will tell you later on. What happens if we increase the number of particles in the system? So we go to, this is 2 to the power 11, and you go to 2 to the power 13, or 2 to the power 15. What we observe is that there is a shift of this transition region towards lower wave numbers, right? So this is exactly what and this has been reported in a paper by Mattheis et al. In a PRL paper. Okay, if we can also compute from our numerical simulations the profiles, the energy profiles or temperature profiles, what we expect if Fourier law hold is something, some straight line like that, but this is not exactly what happens. However, interestingly, if we, for example, use a filter and compute the energy or the temperature considering only high wave number modes, okay, what we obtain is that we obtain something which is very close to a Fourier profile. So the high wave number modes are the one that are works according to the Fourier law, and then there are the low wave numbers modes, which are we call it ballistic, in the sense that they travel from one thermostat to the other without interacting with the other waves. So they don't transport. This is not really a transport of heat as it is required by the Fourier law. We can compute conductivity, okay, so kappa E from numerical simulation, we can compute the fluxes, and then we can compute then the conductivity, and this is in agreement with many other work that has been done on the subject. There is a scaling which goes like n to the n over 5, so 0.4, okay? So, I mean, in somehow we reproduced previous results. We obtained the same scaling as other people obtained with the same model. However, what we found that using our way of analyzing that, we have found that there are these low wave numbers mode that behave very differently from what we expect. Okay, so this is what we observe from a pure microscopic point of view, and now we go to the wave kinetic approach. Okay, so we go to the wave kinetic approach, so we need to build the wave kinetic equation. And let me just sketch how we derive, okay, wave kinetic equation. As I mentioned, it's not a rigorous derivation, but the first thing to do, of course, is written in Fourier space, is to introduce variable, this normal variable AK, which is a combination of QK, which are the Fourier amplitudes of position, and PK, which are the amplitudes of Fourier amplitudes of momentum. This variable AK has an interesting property. I just would like to point this out to you because then I will discuss this. The fact that for K greater than 0, waves travel to positive X, positive direction, and for K less than 0, they travel to negative direction, okay? Then what you do, you write down equations starting from the FPUT problem, the equation that you have seen before. You write down an evolution equation for variable AK, and this is indeed what you get. And this is what we call also the Zakharov equation in the field of surface gravity waves. There is a difference here. Here you have a Kronecker delta that should be interpreted as this Kronecker delta should be interpreted as mod n, because here you have, since we are in a discrete lattice in physical space, what happened is that we have those what are called the unclapped scattering. So which means that, for example, if you have three-way numbers that are interacting and the four-way number is outside the K max, okay, K max, then this, what happened is that this way number is flipped over, so it's unclapped, and it goes back to the brilliant zone. Okay, so this is still deterministic. What we have done also, we have removed using canonical transformation all non-resonant terms, because there are also other non-linear terms in the beta FPU system, but here we have removed them through a canonical transformation, which is valid only for small beta. So it's a near identity transformation that we use. And this is the starting point to derive kinetic equation, okay? So we move to, well, angle action variables, at least those variables diagonalize the linear part of the equation. So in this way, so it's square root of ik times e to the I minus I theta k. And then we write down, there are different ways of doing this. This is the way I do it. We write down equation for action, an equation for angle, and then we expand angle and action for in powers of beta. Beta is the nonlinear parameter. And then this is statistical theory, so we take random initial data, which are characterized by random phases and random amplitude, and we take averages over of the action over initial random phases and random amplitude. Then we take the large box limit. So the idea is to go from a discrete system to a continuous system. We're discrete in Fourier space. We take the large box limit, which means that now the Fourier space becomes continuous. Okay, so the sums will become integrals. Just one comment, in physical space, we are still discrete, okay? We're discrete in physical space, but we're continuous in Fourier space. And then we define the wave action spectral density function in this way. And then we have the evolution of this function, and kt is the wave kinetic equation. Rigorous, as I have said before, there is a rigorous derivation by Deng and Zahir. It's in the archive 2021 in NLS with the dimension greater equal than 3. And this is what it looks like. So it looks like a Boltzmann equation. I'm sure many of you are familiar with this. So it's dn over dt equal collision integral. This collision integral is written here. Just one thing for those who are used to collision integrals, this does not extend from minus infinite to plus infinite, but it extends from 0 to 2 pi, again, because our system is discrete in physical space. We have two delta functions here, now Dirac delta functions here. One is over wave numbers and the other is over frequencies. There are two conserved quantities. One is associated with the delta function over frequencies. Okay, so this is the energy. And then the total number of particles is also conserved. Momentum is not conserved. So even though there is a delta function here over wave numbers, it is not conserved. And the reason why it is not conserved is because of the presence of unclapped processes. What we know a lot of things about this kinetic equation. There is an H theorem, so you can define an entropy, which is the logarithm of n of kt in decay, integrated in decay. And ds, the variation of the entropy in time, is always greater or equal to 0. And it's equal to 0. When it is equal to 0, then we have the so-called Rayleigh Jeans distribution. The Rayleigh Jeans distribution, which is has two parameters which are fixed by initial conditions and which play the role of temperature and chemical potential. Just one remark, because I have worked on this. It is interesting to notice that within this framework of kinetic description, it is straightforward to introduce negative temperatures, negative absolute temperatures. Just if you start with some initial conditions which have a chemical potential which is sufficiently large, okay, then because omega k is bounded in the interval 0 to pi, okay, then this denominator becomes negative. And of course, n of k must be positive, and then temperature is negative. So this system naturally includes the description of negative temperatures in the system. This is just a plot of the Rayleigh Jeans distribution. If mu is equal to 0, this is the classical equipartition. This is some equipartition of energy among the different degrees of freedom of the system. And then this is just a plot of two different cases with mu different. This is minus 0.1. And then the last one is just an example of negative temperatures. When you have negative temperatures, there is accumulation of energy at mode, at high wave numbers, so at mode pi. Okay, but so this is the wave kinetic equation, but we are what we're really interested in is the problem of transport. So we need to include some non-homogeneities in the system because we want to study the problem of the two thermostats within the wave kinetic equation and see if the wave kinetic equation is compatible with microscopic dynamics. Okay, so this is really an important question to answer. And so the way to do it, okay, to include some non-homogeneities in the system is to start with this correlator AK1, A star, K2, and then you have this, what happened in the homogeneous case, K1 is equal to K2, so you consider just, if you see this as a matrix, in the homogeneous case, you consider only the diagonal terms. But if your system is not non-homogeneous, also terms out of the diagonal may become important. So if you Taylor expand dispersion relation around for K1 equal to K2, you end up at leading order with this extra term, which is the advection. So basically, this is the standard, let's say, Boltzmann equation for phonons or kinetic equation with this transport term. And V of k is just the omega in decay, so it's the group velocity of the system. Within this model, there has been some results on the anomalous conduction using this wave kinetic equation, and I just mentioned some of them. There is a paper by Pereverzev, I think he was the first one, discussing anomalous conduction within the Peierls equation, but also Lucarin and Spon, and also more recently Mellet and Merino Seituno did some work on it. And probably there are some other references, but I those are the most relevant. What they all did is they linearized the collision integral. So of course they did analytical work, very interesting analytical work, but they used a linearized collision integral, and they were able, using also Green-Kubo formulas from statistical mechanics, to estimate the exponent of the conductivity, the anomalous exponent of the conductivity, which turns out to be 0.4. So kappa E is like L to the 0.4 according to this work. And but what we do now is, as I mentioned, this is only for what they did is only for linearized collision integral. We decided to do full numerical computation in the presence of two thermostats of the wave kinetic equation. So in order to do that, we have to solve the collision integral. And to do that, of course, it's not so simple because we have multiple integral, you have two delta functions. Of course, you can remove one and you remove one integral. And then you are left with a delta function over frequency, but you can exploit the properties of the Dirac delta function. And it turns out the integral becomes a sum over all the roots of this function gx, which is all roots of the delta omega, which is the sum of frequencies. So delta omega is omega 1 plus omega 2 equal to omega minus omega 3 minus omega 4. So basically this integral is made only around the resonant manifold, and the resonant manifold has been computed analytically. This is a result from Luccarin and Spohn. So there are analytical, well, there are solutions which are, the first three are trivial solutions. First one correspond to all wave numbers that are the same. The second and the third correspond to two equal wave numbers. And then there is the last one, which is non-trivial solution of resonant manifold, which given wave numbers K1 and K3, it is possible to find wave number 2, and this is the analytical function for that, that satisfy both conservation of momentum and conservation of energy. So then, of course, if you use that, you can reduce your collision integral, your multiple collision integral to a single one, and this is now something that is more feasible from a numerical point of view. So at the end of the story, we solve just one single integral in the equation, and I'll give you some examples just to show you that things work, we start, for example, this is just an example. We start with a numerical simulation with an initial condition of time t equals 0. This is the homogeneous case, okay? Before going into the non-homogeneous case, we wanted to make sure that we're able to solve accurately the wave kinetic equation in the homogeneous case. So you start at time t equals 0, with any function, okay, any smooth function here, you let the system evolve. From time t equals 0, you can compute the temperature and the chemical potential of the system, and then you can compute the solution, the Rayleigh-Jeans solution, analytically, and this is the black line, and then you see that the system evolves towards the analytical solution. So this is first result, numerical result. Of course, entropy behaves well in the sense that entropy grows, until stationary state, at least it reaches a stationary state, and the stationary state corresponds to the Rayleigh-Jeans distribution. We have conservation of energy, okay, so this is just an example to show you that when we conserve, our scheme conserves very well energy. We do less well with the number of particles, which should be a conserved quantity of the system. Conservation of number of particles increase by increasing the number of Fourier modes in the system. So if you increase the number of Fourier modes, we have seen that we are able to do much better with respect to the conservation of the number of particles in the system. Just another numerical simulation. suppose that we start with some initial condition, which is the green one, then you let the system evolve, and then you see that there is the formation of these two peaks right here at very low wave number, so k equal to pi or k equal to 0, and it takes really huge amount of time for those peaks to relax to the Rayleigh-Jeans distribution. And the reason for that is that the collision integral, and now you can start putting things together, the collision integral, if you write the collision integral in this way, in a sort of a way in which you have some relaxation time, okay, and this has been done by Perverzev, this is a relaxation time, and you compute this relaxation time analytically, and this has been done again by Perverzev in the limit of at equilibrium, okay, and we have done it numerically to confirm the results. It turns out that this relaxation time diverges, so becomes larger and larger, like k to the -5 or 3 for small k. So this means that the collision integral is very inactive in for small wave numbers. Okay. Okay. So let's now discuss the problem of the two thermostat. Okay. Let's discuss the problem of the two thermostat. Now we do numerical computations of the wave kinetic equation with the transport term in presence of the two thermostat. So we have two thermostat, temperature T1 greater than T2, which are placed at a distance L. How do we model the thermostat? Well, we take two Rayleigh-Jeans distributions with two different temperatures and the same chemical potential. And we use this as a boundary condition. So our boundary condition N, which is the wave action spectral function, has boundary condition on x equal to 0 as Rayleigh-Jeans distribution with temperature T1, and at x equal to L, you have another Rayleigh-Jeans distribution with temperature T2. Now, we have done a lot of work trying to find what is the best scheme in terms of time and accuracy. And interestingly, we also use Runge-Kutta for order, for evolution in time. But interestingly, the Euler method in time works perfectly. And also the derivatives in x, there is this term dn over dx, it's just computed using a first order upwind scheme. We have tried again second order or third order, but things do not change. It's just that they make simulation longer. Okay, so let me just show you what are the results of our simulations. I have to explain you what these plots are. Here we have in colors, we have energy, okay, the energy of the field, which is strictly related to the temperature. Then you have, for x less than 0, you have a thermostat, okay? And from x greater than 0, you have another thermostat, which is colder. So you have two thermostats. And then for each x, as I told you, n is a function of x and k. So there is a Fourier spectrum. For each x, there is a wave number spectrum, right? So you have x, and then vertically you have k. So for each position, you have a wave spectrum, wave energy spectrum. There is this black dashed line here. And as I mentioned you, there are waves that from 0 to pi, they travel from left to right. And from pi to 2 pi, they travel from right to left. Okay, so this is the configuration at time t equals 0, in which we put in the field something which is an average temperature in between the two thermostats, and then we let the system evolve. Interestingly, what we observe is that there are the long waves modes, they start traveling, and you see the formation of the front that travels from the hot thermostat to the cold one, and there is a front that is traveling from the cold thermostat to the hot thermostat. Okay, so this is what is happening. And in this case, for L small, it seems that the collision integral is unable to thermalize locally the system, so that the collision integral is not strong enough in this case to thermalize locally the system. So this simulation is mostly dominated by ballistic modes that travel from one thermostat to the other, basically without interacting. Now, if we, we can compute the energy profile from the wave kinetic equation. We, of course, according to Fourier law, you would expect something that goes from this value to this value with a straight line, but this is not what is happening, because as I have shown you also for the deterministic simulation, there is some sort of a straight line, but then there is a big jump. From the thermostat to the first point in the simulation. Here is another simulation at a different time. So L equal to 10. So we take the distance between the two thermostats is getting larger and larger. And you still see the formation of the front, but you still, what you should be able to see is the fact that with respect to the previous simulation, the collision integral seems to mix, to start taking place or to be relevant. And it seems to, I mean, once you reach some stationary state, seems that at least there are some wave numbers, which are high wave numbers, which around mode pi are in a local equilibrium, okay? And this is the energy profile. So we can compute the energy conductivity as a function of time for all simulation. We run a number of simulation from L equal to 1 to L equal to 500, so very distant thermostats. And so we compute the fluxes, and from the fluxes we compute the coefficient. Of course, it is only relevant once it has reached a stationary state. But you can see from our numerical simulations that the conductivity coefficients also in the wave kinetic equations are a function of the distance between the thermostat. However, if you scale all the coefficients with L to the power 0.4, you have that most, at least those with L larger than 10, they all collapse in a single curve, okay? So this means that if we plot the thermal conductivity as a function of L, it turns out that there is a nice power law, at least for L large enough, which is consistent with the microscopic simulation that we have done, and it's also consistent with the work of Spohn and Lukarinen, who calculated it using the linearized collision integral. Let me just go quickly to the conclusions. And what we have done, we have you consider the beta FPUT problem and then study the anomalous conduction using both the deterministic and wave kinetic simulations. First of all, we have developed a code for the wave kinetic equation, and we have seen that the Rayleigh-Jeans distribution has been verified for a number of initial conditions. Then we have considered the problem of the two thermostats, and again, the wave kinetic equation displays very good agreement with deterministic simulation, displaying this anomalous conduction, which is mostly related to the fact that these low wave number modes travel from one thermostat to the other without any interaction. And of course, then the wave kinetic equation is a really good candidate for developing a macroscopic theory for anomalous conduction. Okay, just one more remark. Because last week we have discussed a lot the hydrodynamics of integrable system. Let me tell you that if we use wave kinetic equation for an integrable system, you would basically get nothing in this, in the sense that the collision integral is for integrable system like the total lattice, for example. You can, for example, in the limit of small nonlinearity, you can formally derive, after removing the three wave interactions, you can derive the wave kinetic equation. Okay, that's something that can be done. But what I have checked, this is quite interesting and remarkable, is that for the total lattice, this coefficient T1, 2, 3, 4 is identically 0 on the resonant manifold. So this coefficient that weights the interaction is 0 on the resonant manifold. So there is no, I mean, thermalization within in the framework of the wave kinetic equation. So it would be only ballistic transport. The same thing happens for KdV equation, and this is a work that we have done with Zahara, which, well, the four wave interaction, there are only trivial solution for the KdV dispersion relation. So, I mean, for integrable system, the wave kinetic equation does not provide the good tool for studying transport in this kind of systems. Okay, this is it. Thanks a lot.
And thank you very much. Thank you very much, Miguel. So I think that we have time for some questions from the audience.
Can I ask a quick question?
Yes, please unmute yourself.
Yeah, thank you for the nice talk. So can I, so is the understanding correct that the basic transport at large wavelength occurs because there's essentially a momentum conservation that occurs at large wavelengths, and you don't see?
Yeah, exactly that. I have not discussed that, but I'm working on that. Indeed, momentum is not exactly conserved by the equations because of the unclapped scattering process, right? However, the long waves do not suffer from this, and they travel. I mean, so momentum, I guess, is fully conserved. So in order to write down, and this is what I'm doing, if you want to write down an evolution equation, macroscopic evolution equation, you should take into account momentum conservation at least up to some wave number.
Yeah,
so
thanks.
This is indeed, I think you pointed out the right thing. I mean, this is what is missing in the picture. And indeed, what I have not done I mean, it's not rigorous, but the idea is that you have some equations which are of the form of like wave equation, which are diffusive. So d temperature over d time plus c dt over dx equal to double second derivative of temperature, right? So it's a wave and diffusive equation at the same time.
Yeah, some kind of a hydro plus diffusive equation.
Yeah. I think that would be. I mean, I already worked out some solutions of this problem, and it turns out that they display these anomalous profiles of temperature that are typical of this simulation that I have shown you.
And is there a relation with Spohn's theory of nonlinear fluctuating hydrodynamics?
I mean, the one that you mentioned is, as I mentioned, this is all for weakly nonlinear systems, so there are no solitons here. Concerning fluctuating hydrodynamics, it's hard to tell. I mean, I have tried to read the papers by Spohn, and I'm not sure I got all. But he has a prediction of the scaling exponent, which is 0.5, I think. So it's not.
It's not divide.
Exactly that.
Because he gets kind of KPZ, or depending also on the various assumptions on some susceptibility the other classes. Yeah,
he writes down directly. I mean, Spohn, he writes down directly the equation, the macroscopic equations. So he has to do it.
Thanks.
Thanks for the answer. Other questions? Well, I have a tiny curiosity, which is not directly related to what you presented, which is like my minor curiosity. You mentioned the work by Deng and Hani, and and they proved the result for dimension 3 or larger. So yeah, okay. So what goes wrong? So is it what goes wrong for a smaller dimension?
It's 135 pages.
I know. So and so it's not even directly connected to what you said, but okay. So just if you happen to know.
I questioned myself also. You know, I when I saw that, I said, okay, it's written in the abstract. I say, what's wrong? But I don't know exactly. They need to control a lot of things in this rigorous derivation. So I'm not sure at what point of the derivation they need to do this hypothesis of But it's, I mean, this paper has received a lot of attention, and he's making a number of seminars. And if you're interested, there is one in a couple of days, and in which he will go through the derivation of the kinetic equation. So if you're interested, I can send you the link, and because this is all in the Simon's collaboration, because there is a big project founded by Simon's Foundation, which is named Wave Turbulence, indeed. So there are a lot of people working in the wave turbulence, including myself. Mostly are mathematicians. I'm a physicist, but mostly are mathematicians, and they are really interested in proving on a rigorous proof of the wave kinetic equation. Even though we, as a physicist, we take it, for granted. We have been using it, and people use kinetic equation for doing wave forecasting, for example, in the ocean. So every day, apart from meteo forecast, you have also the wave forecast, and they integrate the kinetic equation for waves. So we use it all the time.
Okay. Okay. Thanks a lot for the answer, Miguel. So if there are no other questions, I think that we are concluding here the live streaming and recording.